Hi everyone, and welcome back to yet another AP Calculus video. Today we're going to discuss how to find lengths of parametrically defined curves. Now remember, a parametrically defined function is simply a way of describing a function in terms of specifically its left, right, and up-down movement in a two-dimensional plane. So we essentially have an equation for the x-coordinate and an equation for a y-coordinate, and it's driven by this kind of invisible hidden parameter that we like to refer to as t. So as t changes, x and y will change differently, and you can create some really cool looking shapes. And so this is one example of the type of shape, and it's an asteroid, and I'm not sure why. Maybe I spelled it wrong. This is how the textbook spells it, so I don't know. Maybe the textbook editors are incorrect. But you have a graph here. It's called an asteroid. And let's just see. Now I'm curious. Here's our fun aside, right? Oh, it is an asteroid. And I always thought that's how it was spelled, but in our textbook it was asteroid. So I don't know, maybe there's a special name for these graphs and it's just asteroid. In any case, here we go. This is a special graph, and it's created by these parametric functions here, and they're graphed from 0 to 2 pi. Now, we run into trouble when we're trying to find some things, find out information about this, because you can see that if we were to try to find, like, calculus-y things like area under curve, you'd have positive and negative area that would kind of cancel it out. It's just this weird situation. So sometimes when we have a parametrically defined function or a function that is unique, and we're going to get into polar functions later on, and polar functions will behave in very much the same way, in that when you look at the graph and you see that it has some symmetric properties, sometimes what we need to do in order to truly find information about our curve, like the length of the curve or the area under or the area enclosed, we'll need to investigate it a little bit differently, and we'll need to use that property of the graph being symmetric to help us break it apart and be able to determine, for example, the perimeter of this asteroid. So let's suppose that we want to find the perimeter of the asteroid that we saw above. We would need to use a length of curve formula. So right here, this is our length of curve formula. And we're going to see this come about in different ways. For example, in the next unit, we're going to be talking about how parametric equations, we're going to start referring to them as vectors, because a vector is a directed line segment, and we're going to be dealing specifically with velocity, position, and acceleration. And we're going to talk about those types of vectors. But essentially, they're all parametric equations. And so this formula is going to get translated into, in distance. We wouldn't call it a length of a curve. We'd call it the distance traveled by the object, the total distance. But for here and now, in a very general sense, remember we're generalizing. This formula here is going to give us our length of our curve. So as the particle travels along, and as I trace, if I were to take snippets and evaluate, well, I would get the length of curve. If this was a string and I stretched it out and measured it on a ruler, that would be my length of curve. But like I said, the trouble is when we deal with this formula, if I'm trying to go from t1 to t2, because I've got those curves and because of the way that the integrals behave, what's going to happen is I'm going to have a lot of space above, and it's going to get canceled out, and it's going to be a little tricky to try to determine. So what we need to do is we need to consider the symmetry of this function. And so when we consider the symmetry of the function, we need to figure out, well, where does my function, begin to repeat? So let's go ahead and take a look here, and I can see that this asteroid has some symmetry, and specifically it's got this symmetry right here, where from the angle, or from, and here we're dealing with sines and cosines, so t is the angle. So here my angle is 0, here my angle is pi over 2. So from 0 to pi over 2, that length is going to be the same as the length in the other three quadrants. So one of the ways that I can work around this is to use the symmetry feature and to evaluate the length of curve. Now you won't always need to do this with every function, but if you do have a symmetric function here, specifically with parametrically defined functions, you'll need to use the symmetry, and you'll see that sometimes it'll work and sometimes it won't. So by breaking it up into just one piece, and then we're going to take that length and multiply it by 4 to get all 4 segments, that's going to give us our total length. So let's give it a try. Now, here is, we're still spell checking along the way. There we go. So revisiting our asteroid, let's notice the symmetry, right? So what we're going to do is we're going to set this up and we're going to find dx dt and dy dt. So dx dt, now remember, this is tricky because cosine cubed is cosine cubed and sine cubed is sine cubed. So we kind of have the chain rule here. So dx dt, I'm going to use the power rule, and then I'm going to use the chain rule. So there's dx dt. dy dt, same deal. It's going to be 3 times the sine of t squared times the cosine of t. So here are my two derivatives. Now, when I try to evaluate them using my length of curve formula, oftentimes this, I'll use my calculator. And I think at this point I would expect you to be proficient in using your calculator to evaluate. So what I'd like to do is I'd like to show you a way that you can evaluate these, not with your calculator, but just by hand. So let's take a look and see how you would be asked to do this by hand. And this would be a very challenging algebraic problem. If you can conceptually understand how to plug it in and use Math 9 on your TI-84, then you're probably where you need to be. But this is the kind of material here. It's these little tidbits that are going to boost you to a 4 and a 5 on your AP exam. So let's take a look. Using my formula from T1 to T2. So I'm only going to go, I'm going to let T1 be 0. I'm going to let T2 just be pi over 2. And then I'm going to take that length and multiply it by 4. So here we go. My integral is going to be this. I'm going to integrate from 0 to pi over 2. And then it's the square root of dx dt squared. So it's going to be 3 cosine squared, oh, it's negative 3 cosine squared t sine t squared plus 3 sine squared t cosine t squared dt. All right, let's do this without the use of a calculator. We can do this. We've got this. We might need a little bit more room though. Hold on one sec. All right, so I'm going to start out by squaring everything. So I'm going to get 9 cosine to the 4th sine squared t plus 9 sine to the 4th cosine squared t. And then I'm going to notice that I can factor some things out. So square root of, I'm going to factor out a 9 cosine squared t sine squared t. And what's left is going to be a cosine squared here. So when I factored out the 9 cosine squared sine squared, I'm going to be left with cosine squared t. And then over here, when I factored out the 9 sine squared cosine squared, I'm left with just sine squared. So I'm going to have cosine squared t plus sine squared t, which we should all be screaming in our mind, oh, that's just 1. There's my Pythagorean identity. So this is just 1. How fancy is that? So here we go. I'm going to go from 0 to pi over 2. And then I'm going to have the square root of 9 cosine squared t sine squared t dt. And that's going to equal, I can square root everything. And normally when you square root things, you should have absolute value bars in it. But because we're going from 0 to pi over 2, we're in quadrant 1, everything's going to be positive. So I really don't need the absolute value bars here. Typically I would use them because the square root of something squared is always the absolute value. That's where that plus or minus comes in. But here we're in quadrant 1, so the 3, the sine, and the cosine will all be positive. So now I've got this integral and I'm ready to evaluate. And again, no calculator, so here we go. We're going to have to use some sort of u substitution. So I'm going to let u be my sine, which means du is my cosine. So my u substitution looks like this. I'm going to integrate 3u du. So that'll be 3u squared over 2. So when I put everything back, I'm going to have 3 times sine squared over 2, and I'm going to go from 0 to pi over 2. Oh, now it's easy. Sine of 0 is 0. Sine of pi over 2 is 1. So I'm going to have 3 halves minus 0. Oh, that's not too bad, right? So 3 halves minus 0 is 3 halves. And then I have to multiply that by 4. So that's the length of the 1 in the quadrant 1. So if I go back up here, it's so much work. Look at my asteroid. This is 3 halves. So 4 times around, 4 times 3 halves is 6. So the length of the asteroid all the way around is just 6. 6 units of whatever we're measuring. So this will be, again, this is the length of the curve just in quadrant 1. So 4 times the 3 halves gives us 6, gives us the whole length. So again, we're using that property of, the length of curve. We're using the property of that symmetry to just find the area in the first quadrant and multiply it by 4. It's not always the case that we need to do that, but sometimes we do. So let's kind of review a few more things here with our parametric equations, and then we'll kind of wrap it up here. So if we're looking for points on parametric equations, so if we're looking for parts of our curve where we have horizontal or vertical tangents, we always want to remember that the derivative of parametric equations is found by taking dy dt and dividing it by dx dt. And so anytime we're looking for horizontal tangents, we're looking for dy dx to be 0. In other words, dy dt would equal 0, and dy dx cannot equal 0, because when you have 0 over 0, that's, nobody likes that. That's no good. So anytime we're looking for vertical slopes, that's when we're looking for a number on top. So anything but 0 for dy dt, and dx dt will equal 0. So if we wanted to find here in this situation points at which the tangent line to the curve is horizontal or vertical, we would simply need to find dx dt and dy dt. So dx dt here would be negative 3 sine t. Dy dt would be 3 cosine t. And we're going to be looking for where each of these are 0. So dy dt, or let's start with dx dt. Dx dt equals 0 when negative 3 sine t equals 0. Well, where is the sine 0? Oh, on my unit circle, it's 0 at 0 and pi. So then we'll do the same thing over here. Where is dy dt equal to 0? It equals 0 when the cosine of t equals 0. So where is the cosine 0? Well, that's at pi over 2 and 3 pi over 2. So there's always going to be, not always, but there's potentially going to be more than one spot with these parametric equations, because again, parametric equations allow us to kind of go in loops and circles. It's kind of fun. So this is what we're looking for. This is how we find horizontal and vertical slopes. Now this is t. We need to now find the location. So we always need the x and the y. So we found the t's. Now let's find the x and y. So we're not quite done. So using my equations, when t equals 0, x equals negative 2 plus, what's the cosine of 0? It's 1. So x is 1, and y will be 1 plus 3 times the sine of 0, which is 0. So you're going to have 1, 1. That's one spot where we have a horizontal tangent. And then when t is pi, you're going to have x equals negative 2 minus 3. That's going to be negative 5. So I'm plugging pi in for t. That's all I'm doing. Y is still going to be 1. So negative 5 comma 1 would be the other spot where we have horizontal. So these are all horizontal. Now to find our vertical, we're going to say, okay, when t is pi over 2, we're just going to plug pi over 2 into our 2 coordinates. So negative 3, so, whoops. And make sure you label everything so you don't accidentally plug it into dx dt like I was about to do. So x equals negative 2 plus 3 times the cosine of pi over 2, that's 0. So x is just negative 2. Y is 1 plus 3 times the sine of pi over 2, which is 1, so that's 4. So we're going to have negative 2, 4. And then when t is 3 pi over 2, x will be negative 2, that would be negative 2 again. And then y would be 1 plus negative 3, so that would be negative 2. The sign is negative 1 down there. So negative 2, negative 2. There we go. So these are my answers. This is where I'm going to have horizontal and vertical tangents. This is just something I wanted to review. I know we hit it in the previous video, but it's always good to go back and revisit these concepts and really make sure we understand. The biggest thing that we want to take away from today, though, is the using this length of curve. Now, 9 times out of 10, you'll be asked to do the setup and you'll show the length of curve. So the key here with the length of curve that we talked about was find that derivative, plug it in and square it. So show the work, show the setup, show the integral. 9 times out of 10, these types of integrals will just be put into your calculator and you'll go math 9. And remember, the handy dandy trick here is if you are going to use math 9 and if you are going to use your calculator, type this into y1, type this into y2, so that you type it in one time, and when you're typing it into that square root, then you just do y1 squared plus y2 squared. So use those tips and tricks to avoid mis-entering into your calculators and ultimately getting the wrong answer. Always show your setup, always clearly label everything that you're working on so that you don't lose track, and then also, more importantly, so that the AP reader who's reading your test and your free response question can follow your work and knows the intention and understands what you're trying to do. You're more likely to get points for things even if they're done incorrectly if you're showing steps going in the right direction. Whatever the case may be, you need to practice this, and without practice you will not become proficient. You need to keep at it, you need to keep going. So do your homework, keep practicing, ask for help when you need it, and just keep going. You can do this. You've got this.